Hello good people, I am tasked with calculating the activation energy for this particular problem. I'm given two data sets and I am given the Arrhenius equation. As always, I like to rewrite what has been given to me and what I need to find out, because that helps me organize my thoughts. So in this particular case, we have two experiments. Experiment 1 and, funnily enough, experiment 2. And experiment 1 was carried out at 823 Kelvin, so I will write T1 for temperature of experiment 1 equals 823 Kelvin. The rate constant for experiment 1 was determined to be 1.1. So I will write K1 for the rate constant of experiment 1 equals 1.1 liters per mole second. And I will do the same thing for experiment 2. It was carried out at 898 Kelvin, and the rate constant was determined to be 6.4. Do not forget the units. If I look over to the right or at my Arrhenius equation, I also have this R. What is R? Well, it is the ideal gas constant. So that is 8.314 joules per mole Kelvin. And I need to find activation energy, EA. That is my target. If I look at the Arrhenius equation on the right, there is a bit of a problem, because that Arrhenius equation accounts only for one value of K, and it also has this A, the frequency factor. Now, I do not know anything about it, which means I need a different version of the Arrhenius equation, and that is this formula here. If you're wondering how in the blazes do we go from this Arrhenius equation at the top to this Arrhenius equation at the bottom, I suggest you look up the next video in the series. For now, I will just keep going. So we're going to use this equation with our values. And we have 1.1 over 6.4 equals the activation energy over the ideal gas constant. And all of that multiplied by 1 over temperature of experiment 2, 898 Kelvin, minus 1 over temperature of experiment 1, 823 Kelvin. Okay, some of the units will cancel over here on the left hand side, which means I will have the natural log of 1.1 over 6.4, which is 0.17. All of that equals the activation energy over the ideal gas constant. And I'm just going to take a shortcut and copy this and place it down here, because I want to focus on the bracket first. So in the bracket we have 1 over 898, which is 0.0011, and the unit is per Kelvin, because we've divided by Kelvin as well, minus 0.0012 per Kelvin. The natural log of 0.17 is negative 1.77, negative 1.77, and all of that equals, again, I'm just going to take a shortcut and scroll down a little bit. Multiplied by, well, 0.0011 minus 0.0012 should be negative 0.0001, and the unit is still per Kelvin. Now, because I'm trying to get the activation energy alone on one side, I'm going to divide negative 1.77 by negative 0.0001 per Kelvin. So if I do that on my trusty calculator, I get 17,700. 17,700, and now the unit is Kelvin. Equals, once again, I'm just going to take a shortcut and paste activation energy over the ideal gas constant. Scroll further down. Now I'm ready to solve for my activation energy. So activation energy will equal 17,700 Kelvin multiplied by the ideal gas constant. And we can see that the units will cancel, Kelvin and Kelvin will cancel, and I will be left with activation energy of, pardon me, let's multiply that, 8.314 multiplied by 17,700 is 147,158 joules per mole, or I could round that and I could say it equals 147 kilojoules per mole. And that is the activation energy for my reaction. That is all for now, and I will see you on the flip side.